So what we're working on today is we're going to go over the unit circle a little bit more. I went over it vaguely with you guys in the 4.1 section, but we are going to start actually doing some work with the unit circle. And then we are going to go over evaluating trig functions. Just the 6 basic trig functions. Have any of you guys done any trigonometry at all that you know of in your past lives in math? Not that you know of. It's not unusual that you haven't. Some of you might have done a little of it in geometry if they got to it. If you've heard of sine, cosine, and tangent or SOHCAHTOA, sometimes geometry classes touch on it a little bit, but unless you move into the higher maths, which are like calculus, which is kind of what we're working towards. Thank you, Ryan. So some of the others might have done it too, and they just didn't remember it until I said those words. And it's all basically triangles. It's all basically the math of right triangles, which makes sense because we're doing trigonometry now, and trigonometry is the measuring of triangles. Physics, you would definitely do it. You use a lot of trig in physics. And it's not a super difficult math, right? But it is its own subject for a reason, because there's a lot to cover. And what we're dealing with these days is we're dealing with something we call unit circle trigonometry. And ultimately what it is the measurement of, we're going to deal with me drawing. I should have just brought in pictures of it. And I did post a full unit circle for you guys for your homework to work off of, because it'll be so much easier for you if you have a fully done unit circle in front of you when you're doing it. Ultimately, what we're saying is, what are the measurements of these triangles when we're discussing a radius of 1 unit, right? So we're saying that this from here to here is 1 unit. Whatever we're measuring that 1 unit in, right? We're saying that this is a length of 1. So our x value here would be 1, and our y value would be 0, right? If this was a point on a graph, this point would be 1 unit and 0 units because we're not going up. This one, right, if we were measuring this one out, let's see if I can make it down the line. So hard to draw a straight line. This is also 1 unit, right? It's still a radius of the circle, but this would be 1 unit on our y value. It went up a unit. This is still 1 unit. It's just in the negative direction, so it would be -1, 0, right? And all of these 1 units correspond to points on a graph, right? If we looked at this one, still 0 on the x, we're not moving left or right at all, but it would be -1 in the y direction. And that's what the unit circle is based on, are these 4 components. But we don't just measure a circle, at 0 degrees, 90 degrees, 180 degrees, and 270 degrees, right? We measure it all the way around. There couldn't be points anywhere on the circle based on this 1 unit piece of information, right? And what we're talking about is triangles. And we're talking about, what if we break this up differently? Now, when we're talking about the unit circle, we focus on certain points within it because we have those special formula triangles. And I don't know if you've heard, like when in the past when you were dealing with right triangles, you'd have the 30, 60, 90 triangle, and then you'd have the 45, 45, 90 right triangle, and they were those special right triangles. If we think about that in terms of if we were to graph them, say I had a point at, let's look at 45s first, right? If we're looking at this right here, this is a 90-degree angle, right? We know that. We've seen it forever. I can draw a line from here to here, and it's a 90-degree triangle, right? Well, what if my 90 was different? What if I divided this here at 45 degrees, right? This is our 90. Because you know this on a circle, right? This can be a 45-degree angle. And if I drew a line down here at 45, a straight line, I would have a 90-degree angle in that direction. And what we're looking at now are what are the points that correspond at these angles. And I can be as long-winded as I want in this explanation, but the truth is I'm going to give you a picture that shows you all of the numbers that you need, right? I just kind of want you to understand what they are. So if at a 45-degree angle, I'm going to have a point on the circle where that tip is going to touch, right? And it is going to have a point that corresponds to it. And I can tell you right now that all 45-degree angles have a point at radical 2 over 2, radical 2 over 2. Now, think about this if I divided this in half as well, right? Because 45 is halfway between 90 and 0. So if I went another 45 degrees right here and I had an angle, this point would also sort of be radical 2 over 2, radical 2 over 2. The difference is everything in this quadrant is positive. Is everything in this quadrant positive? Think about your signs. Are my X's and Y's positive over on this side of the circle? Right, our X's would be negative, right? Everything X on this side of a coordinate plane would be negative, right? So you're going to have the same thing, right? The difference is your X value is going to be negative. What if I drew it here? What if I divided this 90 degrees in half and I drew the line here? My point would still be radical 2 over radical 2. Radical 2 over 2. I can't have radical 2 over radical. But in this case, both would be negative, right? Because here my X's are negative on this side, but also down below the y-axis, my y's are negative as well. So these would both be negative. If I drew it here, my 45, if I divided this one in half, I would still have radical 2 over 2, radical 2 over 2. But in this case, my x's are positive because we're on this side, but my y's would be negative. So nothing changes a whole lot, right? The difference is just in the signs. So if we know this 90-degree angle and all the points in it, all the main points in it, we know it for every quadrant going around the circle. The only thing that's going to change are the signs. So if we looked at that same circle, it's like I can't properly draw without sound effects. So if we looked at this same circle, see if I can do it. Oh, it's terrible. But you can play along. I gave you a much better one. I gave you a full scale one. What if I broke this down into 6 parts, right? 6 parts up here, 6 parts down here, technically 12. Here I broke it into 8. This is still 90, right? This is still 0 or 360, right? This is still 180, 270, right? We could also look at it in terms of pi, which is what we're going to be using more, right? We know that this is 0, this is pi, so this is half of pi, so we could just write it as pi over 2, right? So if I'm dividing this up, say, in what we would call 30-degree angles, right? Or if I want to divide it evenly into 6 parts, I could go that this is pi over 6, right? Or 1/6 of pi. This would be 60 degrees, or 2/6 of pi, which is just 1/3 pi, right? I can divide it up again here, right? This is 3/6 of pi, or pi over 2, 1/2. 4/6 of pi, which is 2/3, right? 5/6 of pi, which is just 5/6. And then we have 6/6 of pi, which is just pi. Do you have to memorize these? You probably should, but I can't make you do it this time. I would train you in this so good if we were in class. I would have you be doing quizzes all the time on how to build this. But at this point, I can't really do that with you because you're far away. So I'm just providing you with a picture of a unit circle, and you will have all of this printed. I just kind of want you to understand how it builds. And each of these spots correlates to a point, an XY point on a graph, right? Every one of these, and we can take it all the way down, right? We have one here, we'd have one here, here, and here. And these would be like 30, 60, 90, 120, 150, right? 180, and they're degrees going around the circle. When we look at the points, though, just like on our 45-degree angles over here where we had the same points, it's going to work similarly when we're dealing with these 30-degree increments, or 1/6 of pi increments. This point right here would correspond to radical 3 over 2 and 1/2, right? Our x value is radical 3 over 2. Our y value is 1/2. What's interesting about this is our 60-degree angle, or our pi over 3, is the opposite. It's just 1/2 over radical 3, 2. So those are always going to be the same. When we look at the other side, think of it, if we're talking about this part right here, think of it as folding this in half on this y-axis. This part right here, this point, think of it as you're counting up from here. It's going to match the opposite side. This point right here would be radical 3 over 2, 1/2. What's going to change on it is what? exactly, our x value is going to be negative, right? This is going to be 1/2 over radical 3 over 2, but our 1/2 is going to be negative. Here we're going to look at it the same way, but now we're going to look at it as flipping it on the x-axis, like we're always kind of counting from this line right here. So if I came down here, this is going to be radical 3 over 2, 1/2. This is going to be 1/2 radical 3 over 2, right? But in this one, everything's negative, right? Because our x and our y are both negative in this quadrant. Here, think of it as counting from this line, right? We're going to have the same thing. We're going to have radical 3 over 2 times 1/2. I mean, sorry, not times. And then we're going to have 1/2 radical 3 over 2. And in this one, we'll have positive x's, but negative y's, right? So this is what I mean by you really only have to memorize, when it comes to it, this portion, right? The 0 to 90 degrees, because everything's pretty much the same going the rest of the way around the circle, right? We're just changing the signs of it. And that's all I'm going to really get into using the unit circle, because I provided you a really good picture, which I'll show you after I go over the trig functions themselves. But what I wanted you to see is that they have, sorry, that got really big really fast. They have very distinct x and y values, right? Every single one of them. Ooh. Sometimes it really sucks being left-handed, right? Every one of these is an xy point, right? This is our x, and this is our y. Every one has a point, right? Even this right here, the line is at an x value of 0 and a y value of -1. So even that is an xy point. Everything has an xy point on it based on that one unit. So that being discussed briefly, we're going to look at our trig functions, our 6 basic trig functions, right? The first 3 you've heard of, right? We have sine. We're going to call it sine of t, right? Some number t. What could that be? It could be 30 degrees. It could be pi over 6. But we'll call that sine of t. Sine is equal to our y value on the unit circle, right? So if I said, what is sine of pi over 6, it would be 1/2. It would be whatever our y value is, right? Cosine of t corresponds to our x value. So if I said, what is cosine of pi over 6, it would be radical 3 over 2. And we'll show you that more as we get going. Now, tangent, I don't know if you remember this from geometry, but tangent is sine over cosine, right? And so it would just be y over x in a fraction, right? And in this case, x can't be 0, right? Because we can't divide by 0. The other 3 kind of correspond to the 3 that we have here. So we'd have cosecant, CSC is cosecant of t, which is just 1 over y. Again, y can't equal 0. Why? Because it's in the denominator, and we can't have a denominator of 0. Secant of t corresponds with cosine. Anyone guess what that might be? If cosecant is 1 over y and it corresponds, it's the reciprocal of sine, secant is the reciprocal of cosine. So it would be 1 over x. Again, x can't be equal to 0. The last one we have is cotangent. So if we had cotangent of t, that would just be x over y. Right? Technically, it's 1 over y over x, but when we solved that all out, that fraction, it would come out to just x over y. And now y can't be equal to 0. And why would we want to know all of this? Well, we can evaluate our functions based on that. So think about if we said that t was equal to pi over 6, right? Let's say we're going to evaluate when t equals pi over 6. Well, if you remember correctly, when we want to evaluate all 6 trig functions at pi over 6, if we looked at that unit circle, right, and we looked at pi over 6, right, which was at about 30 degrees, not even about, that's our pi over 6. We had a point on there, right? If we come over here, that point was radical 3 over 2 and 1/2. So our point is radical 3 over 2 and 1/2. This is our x. This is our y, right? Just like when we plot any point. So when I say I want sine t when t equals pi over 6, it's like saying I want sine of pi over 6. And we know that it is the y value, right? So it's just going to equal 1/2, right? Because that is our y value at pi over 6. If I want to evaluate the cosine when t equals pi over 6, so the cosine of pi over 6, it's going to be our x value, which is just radical 3 over 2. But what about tangent? Tangent of pi over 6 is sine over cosine, or y over x. So it would be 1/2 over radical 3, 2. Cannot leave it that way. I have to evaluate it. But if you remember, when we've got a fraction divided by a fraction, we can just multiply. We have 1/2 times the reciprocal of the bottom. So we flip them, right? So it would be times 2 over rad 3, which is going to give me 2 over 2 rad 3. These are going to cancel out. I'm left with 1 over rad 3. Can I leave a radical in the denominator? I'm taking you back to algebra 2. If you got this far, I'd be like, yay, but I'll only give you half credit on this piece of the problem, right? You have to rationalize the denominator. And all that means is I have to multiply the top and bottom times whatever that radical is, right? And I would get rad 3 over 3. It works every time, just whatever that radical is, multiply the top and bottom by that. And it's called rationalizing the denominator because you can't have a radical in the denominator. Here's the thing. We are set out to evaluate all 6 trig functions. So we also need to look at the cosecant, right? And the cosecant is 1 over y. So if we're going to do that, we're going to go cosecant of pi over 6 equals 1 over y. Well, that's just 1 over 1/2. Can't leave it like that. So we're going to multiply 1 over 1 times 2 over 1, which is just 2. What's next? We have secant of pi over 6. Well, that's just 1 over x. Right? It equals 1 over x, and we know our x is rad 3 over 2. So we're going to do the same thing. We are going to rationalize all that, right? We're going to have 1 over 1 times rad 3. By times 2 over rad 3, because we need to do it by the reciprocal. And we're going to get 2 over radical 3. Can't leave it like that. So we have to multiply rad 3 times rad 3, and we get 2 rad 3 over 3. So is this a pain? Absolutely. Is it tedious? Absolutely. But it's not difficult. Here we've got cotangent of pi over 6. That is our last one. What do we know about cotangent? Well, it's 1 over tangent, right? We could just say sine over cosine, but technically it's 1 over tangent. We can look at it that way. If we look at it as 1 over tangent, it's 1 over rad 3 over 3. Right? If we looked at it as sine over cosine, it would be 1/2 over rad 3 over 2. But either way, works out. We got 1 over 1 times 3 over radical 3, which is going to give me just 3 over radical 3. Can I leave it like that? No. So I'm going to multiply by rad 3 over rad 3. And I get 3 rad 3 over 3. And look what happens here. These cancel. And I just get radical 3. You will see these over and over and over again. They will all work out the same way. Sometimes you will have a negative, and I made sure that you absolutely do have a negative at some point. Let's look at these in terms of trying to find you a good negative one to work with, but negative pi over 3. So if I look at this in terms of, let's just look at the first 3 trig functions, right? Sine, cosine, and tangent. Let's look at evaluating sine of t, cosine of t, and tangent of t when t equals negative pi over 3. Well, first of all, what is negative pi over 3? What does that look like? What it's going to be is, if you notice up here, we have pi over 3, right? Negative pi over 3 is the same distance in the negative direction. So it's going to be this point right here, 1/2 and negative rad 3 over 2. Does that make some sense? It would be this point right here. And it would be positive 1/2, because that's our x values in the positive, and negative radical 3 over 2. And this would be the x, y value that we're working with when we evaluate these. So if sine over t is y, it's just negative rad 3 over 2. If cosine of t is x, which it is, it's just 1/2. Tangent, we know, is sine over cosine. So it would be negative rad 3 over 2 over 1/2. And we would have to work with that, right? It would be negative rad 3 over 2 times the reciprocal of the bottom, which is 2 over 1, which just gives us 2 rad 3 over 2. And we can cancel these and we just get radical 3. And so we can do this with all of them, right? Does that make some sense to you? All of your answers are there. It's just how you're going to manipulate them. Does that make some sense? As long as you know what your x, y value is, then it's just solving these out. Did I lose you guys? Are you mentally still with me? I know it's early for all of this. You there? All right. Well, I'm not gonna give you any more examples unless you guys let me know you need them as we go. I'm gonna stop this recording right now.